Distance seems like the simplest, most honest thing in physics. You want to know how far it is to the door? You grab a tape measure, stretch it out, and read the number. 14 feet. Done. Nobody argues about it. Nobody writes philosophy papers on it. 14 feet is just 14 feet. You want to know how far it is to the moon? You bounce a laser off a mirror left by astronauts and time how long the light takes to come back. About 239,000 miles. It's clean, solid, and clear. It feels like the one measurement in all of science that never lies. Actually, that's completely wrong, and I can prove it. I used to feel that same way. Distance felt like bedrock. You stand here, the wall is over there. The gap between you and that wall is a fact about the universe, not an opinion. It's a physical fact that exists independent of you, whether you look at it or not, whether you walk toward it or run away. That gap has a specific size. For a long time, the smartest people who ever lived agree. Euclid built his entire system of geometry on this idea. The whole thing rested on the notion that space is a fixed, rigid, eternal container. Lines have definite lengths. The angles of a triangle always add up to 180 degrees. The distance between 2 points is the distance between 2 points, period. Newton felt the same way. He needed a state for his physics, and that fixed Euclidean space was it. He called it absolute space, a vast, invisible, unchanging grid. Objects move through it, and forces push them around, but the grid itself is permanent. Those distances are written in stone. Honestly, this worked incredibly well for over 200 years. Engineers built bridges using that geometry, and the bridges didn't fall down. Ships navigated oceans with it. The whole Industrial Revolution was built on the assumption that a foot is a foot, everywhere and always. So, what's the problem? The problem is that nature doesn't care about your tape measure. Let me set the scene. It's 1905. A young clerk in a patent office in Bern, Switzerland has been thinking about light. Specifically, he's thinking about something strange hidden in the equations of James Clerk Maxwell. Those equations imply that light travels at a fixed speed, about 186,000 miles per second. The bizarre part is that this speed doesn't depend on how fast the light source is moving, or how fast you are moving when you watch it. That's very strange. Normally, if I'm on a train and throw a baseball forward, you standing on the platform see the baseball moving at the train's speed plus my throwing speed. That's just how speeds add up. But light doesn't play by that rule. Light always arrives at that exact same speed, no matter what. This young man, Albert Einstein, took that fact incredibly seriously. He asked, what has to change about our understanding of space and time for the speed of light to be exactly the same for everyone? The answer shook the foundations of science. Here's what he found. Imagine two people. One is standing on a train platform. The other is riding past on a super-fast train, moving at, say, 80% of the speed of light. Now, this isn't realistic, but that's how thought experiments work. You push things to the extreme to make the effects visible. Both people have rulers. Both are measuring the length of the exact same object, let's say, a boxcar on that train. The person on the train lays her ruler down next to the boxcar. She's careful and precise. She says it's 40 feet long. The person on the platform watches the boxcar fly past. He makes his own measurement, corrects for the time it takes light to travel, and fixes every conceivable error. He gets a different number. He says it's 24 feet long. They argue. They check each other's math. They bring in other physicists. The verdict comes back. Both measurements are correct. The boxcar is genuinely 40 feet long to the person riding with it, and it is genuinely 24 feet long measured from the platform. These aren't mistakes. These aren't optical illusions. When you remove every possible source of confusion, the disagreement remains. The distance is truly, physically, undeniably different depending on how fast you are moving relative to what you're measuring. This is called length contraction. The faster you move relative to something, the shorter it gets in the direction of motion. At everyday speeds, like a few miles per hour, the effect is too tiny to measure, but as you get closer to the speed of light, it becomes dramatic. At 99.9% of light speed, a 100-foot object shrinks to about 4.5 feet. The object itself doesn't feel squeezed. In its own frame, it's normal. But to you, looking at it fly past, it's compressed to almost nothing. Think about that for a second. Distance, the most trustworthy quantity in physics, just became a matter of perspective. It depends on how you are moving. It is not a fixed fact about the world. It is a fact about the relationship between you and the world. That is a completely different kind of thing. You might try to save the situation by saying, well, one of those must be the real one. The measurement where the boxcar is sitting still, that's the true length. But relativity says no. There is no special preferred frame. The laws of physics work the same in all of them. The person on the train is just as much right to say she's sitting still and the platform is the one zooming by. From her perspective, it's the platform that's contracted. Both are right, which means neither has the real distance. There is no real distance. There's only the distance according to each observer. That is the revolution. But wait, maybe you're thinking, fine, things get weird near light speed. That's exotic, but it doesn't affect my morning commute. And you'd almost be right. Almost, because the trouble doesn't stop with that theory. 10 years later, Einstein publishes General Relativity. And this theory doesn't just say that distance depends on your speed. It says that distance depends on what else is around you. Imagine you're floating in deep space, far from any star. You stretch a rigid rod between two small markers you've placed in the void. You measure the gap, 10 meters. Solid and reliable. Now, I take a massive star and park it right next to your markers. The rod looks the same. But if you try to verify the distance by timing a light pulse bouncing between the markers, you find the light takes slightly longer than before. The space between those markers has expanded. It's not because anything moved. The markers are right where you left them. The space itself, the physical geometry of the area between them, has been changed by the mass of that star. Near a massive object, the rules of Euclidean geometry break down. Parallel lines bend toward each other. Angles of a triangle don't add up to 180 degrees anymore. Distances measured through curved space are longer than they look on a flat map. It's as if the space near a heavy object is deeper than it appears. Near a black hole, this becomes monstrous. Two markers that look only a few miles apart from a distance might have an enormous actual distance between them. You would fly and the destination wouldn't get closer, because every meter of space is stretched by the extreme gravity. Geometry becomes unreliable. Map and territory do not match. Now, if I were a student in the audience, I'd raise my hand and say, Professor Feynman, this is dramatic, but I've got a ruler right here. It says 12 inches. It said 12 inches yesterday, and it'll say 12 inches tomorrow. What's the problem? And I'd smile because he's making the exact same argument Newton would have made. He's right. In everyday life, distance works perfectly. But so does the idea that the Earth is flat, as long as you never leave your neighborhood. The question is not whether the approximation works. The question is whether it's the truth. And those are very different things. Let me make it worse. Let's zoom all the way out to the entire cosmos. In 1929, Edwin Hubble measured the light from distant galaxies and found something that changed everything. The farther away a galaxy is, the faster it is moving away from us. This looks like an explosion, like we're at the center of some big blast and everything is flying outward. But that's entirely the wrong picture. The galaxies aren't flying through space. The space between them is growing. New distance is being created, manufactured right in the gaps, moment by moment. Space itself is stretching, and it's been doing it for about 8 billion years. So, when I tell you that the Andromeda Galaxy is about 2.5 million light-years away, I'm already in trouble. Which 2.5 million light-years do I mean? The distance right now? The distance when the light I'm seeing left Andromeda? The distance it will be by the time I finish this sentence? These are all different numbers. For very distant objects, the differences are huge. A galaxy whose light has been traveling for 12 billion years is not 12 billion light-years away today. It's actually more like 30 billion light years away right now. Because space has been expanding the whole time that light was in transit. That 30 billion light year number is just a calculation. Change your assumptions about the expansion rate and you change that number. Astronomers actually use 4 or 5 different definitions of distance for faraway objects. There's the light travel distance, the proper distance right now, the distance based on how big an object appears, and the distance based on how bright it looks. For nearby things, these all give the same answer. But for a galaxy near the edge of the observable universe, these numbers can differ by factors of 2 or 3 or more. Which one is the real distance? None of them. Or all of them. Each answer is for a different question, and none of them is the single, simple Euclidean number you wanted. Distance on that scale is not something you measure. It's something you compute, and the answer depends on which question you are really asking. By now, that old idea of fixed distance is in ruins. A ruler between 2 points doesn't give you a fundamental fact about the universe. It gives you a number that depends on your speed, the gravity you're in, the history of the cosmos, and your definition. So, I owe you something better. Let me rebuild. In special relativity, there is one quantity that everyone can agree on. It's not distance, and it's not time. It's a combination of the two. It's called the space-time interval. Imagine 2 firecrackers go off, one here and one over there, a few seconds apart. You and I might disagree about how far apart they are in space. We might disagree about how much time passed between them. But if we both compute a particular combination time squared minus distance squared, we get the exact same number. Every observer agrees on that interval. That is the real thing. Think about a tall flagpole on a sunny day. In the morning, the shadow stretches long to the west. At noon, it's short. In the afternoon, it reaches east. The shadow keeps changing, but the flagpole itself doesn't. The pole has a fixed 3D height. What changes is the projection of that height onto the 2D ground, and that projection depends on the angle of the sun. Distance is like that shadow. When you measure a distance, you're just projecting that fundamental space-time interval onto the space part of your particular frame of reference. This means space and time are not separate things. They are woven together into a single 4-dimensional fabric, space-time, and the true geometry is the geometry of space-time, not the geometry of space alone. Minkowski saw this back in 1908. He said, "Space by itself and time by itself are doomed to fade away into mere shadows, and only the union of the two preserves an independent reality." He was right. In general relativity, space-time gets even richer. Mass and energy don't just change the distances we measure. They reshape that entire 4-dimensional fabric. Geometry is not fixed. It is dynamic. It responds. Think of the ocean's surface. If you want the distance between 2 boats, you might stretch a rope across the water. But the surface is moving. Waves lift the rope and troughs drop it. Calm water gives one answer. A storm gives another. Space-time is like that. It's not a still pond. It is a living surface where geometry rides the waves of matter and energy. Now, one more step. This is the most unsettling one: quantum mechanics. In the quantum world, distance gets weird in a completely different way, having nothing to do with speed or gravity. Take 2 particles in a special, linked state. We call it entangled. Their properties are linked on a fundamental quantum level. Then, you separate them. One stays here, and the other travels to the other side of the galaxy. It doesn't matter how far apart they are. If you measure one of them, check its spin, for instance, you instantly know the spin of the other one. Your first instinct might be that they were programmed in advance, like a pair of shoes. If you find the left shoe in one box, you know the other box has the right shoe. What's the mystery? But in 1964, a physicist named John Bell worked out a mathematical test to check that programmed shoes explanation against something genuinely stranger, and the experiments, done many times since, have come down on the side of strange. The connection between entangled particles is stronger than any programming could produce. The measurement on one particle is affecting what you find on the other, and the distance between them makes no difference. 1 meter, or 1 billion light years. The connection doesn't weaken or fade with distance. Entangled particles don't experience separation the way planets do. In some real quantum mechanical sense, they are not far apart at all. The concept of spatial distance doesn't apply to them. This doesn't mean you can send a message this way. Causality is safe, but it reveals that the quantum world organizes itself based on connections that have absolutely nothing to do with distance. Two entangled particles across the galaxy are more closely linked than two unentangled particles touching on your desk. And here is where things get truly radical. Some very clever people, working at the boundary of quantum gravity and quantum information, have proposed that maybe space itself is not fundamental. Maybe distance is not a basic ingredient of reality. Maybe it's an emergent property, like temperature. No single molecule has a temperature. Temperature is just a statistical summary of what trillions of molecules are doing. What if distance is like that? What if two parts of the universe are near each other because they are heavily entangled, and far from each other because their entanglement is weak? In this picture, space is not the arena where things happen. Space is the scoreboard. It is a readout of how entangled things are. Cut the entanglement between two regions, and you create a geometric gap, a geometric rift. Distance is not something that exists first. It's something that emerges from the pattern of quantum connections underneath. I want to be clear, this is not settled science. It is a research program. The math works beautifully in simplified toy universes, but we don't have a complete theory that derives our real 3D world from quantum entanglement. But the direction of evidence is remarkable. Every time we dig into what distance really is, it gets less solid, less fundamental. It feels more and more like an approximation of something deeper. So, where does that leave you? You started with a ruler, convinced that the gap between two things is a simple fact. And I've pulled that apart, layer by layer. Speed warps it. Gravity reshapes it. Cosmic expansion makes it a moving target. Entanglement ignores it. Distance looks less like bedrock and more like condensation on a glass, something that forms on the surface of a process we don't fully understand. And yet, tomorrow morning you will get out of bed, walk to the kitchen, and the coffee pot will be exactly as far away as it looks. The floor will be solid. The old Euclidean rules work magnificently at the human scale. Carpenters and pilots don't need to worry about space-time intervals. That's because the approximation is superb within our daily lives. It is practically perfect, but it is still an approximation. The actual geometry of reality is richer, stranger, and more beautiful than Newton or Euclid could have ever dreamed. What keeps me awake, what I find incredibly thrilling, is the question behind all of this. If distance isn't fundamental, then what is? What is the universe actually made of at its deepest level, before space and time even exist? We don't know. Nobody knows. But the fact that we can even ask that question tells me we are pulling on the right thread, and I suspect the real answer will be stranger than anything we have imagined so far. So, next time you look up at the night sky and someone says a star is 400 light years away, ask yourself, 400 light years according to whom? Measured how? At what moment? And if the answer is tangled and complicated, don't be frustrated. Be amazed. Nature's showing you how much deeper it goes than any ruler can reach. That space between you and that star is not just a line. It's a living, shifting thing, dependent on the observer. And the fact that the starlight still reaches you, crossing that ambiguous distance, should feel a little more miraculous. If you had to guess, what do you think space is really made of? I'd love to hear what you come up with.